All right, so now that we know a little bit about the makeup of an atom, specifically the subatomic particles, the protons, neutrons, and electrons, let's take a look at how we can identify and write, and how we note the notation that we use for these different subatomic particles. And what we're going to use as a notation, we're going to write symbols known as nuclear symbols, or sometimes they're called atomic symbols. And these are going to look similar, but also they're going to be slightly different than our normal type of notation for the elements. So let's take a look at a couple of the important numbers to begin with, and then we'll incorporate them into these nuclear symbols. So when it comes to our atoms, we can identify an atom by a couple numbers, by the number of protons, by the number of neutrons as well, and by extension, to a lesser extent, the number of electrons. But we need to know some other characteristics of the atom in order to do that. So the number of protons that are in a nucleus of an atom is known as the atomic number. Okay, so the number of protons is the atomic number. They mean the same thing. And that atomic number is abbreviated Z for atomic number. Atoms, by definition, are neutral. Okay, when you say the word atom, you're automatically saying that thing is neutral. What does that mean? That means that your total positive charges must equal your total negative charges. So remember now, your protons carry a positive charge. And if atoms are neutral, there must be the same number of negative charges. So what in an atom is responsible for the negative charge? Well, that's the electrons. So for an atom then, the number of protons has to equal the number of electrons. So the charges cancel out. Positive charges from the protons cancel out the negative charges for the electrons. And by the way, I forgot to mention this in the earlier table, electrons are often abbreviated E, or E with a negative superscript. Protons are often abbreviated P, small p, or P with a positive superscript. And then neutrons are often abbreviated N, small n, or small n with a 0 superscript. Okay, so these are common notations for protons, neutrons, electrons. Okay, so the number of protons is the atomic number. For atoms, the number of protons equal the number of electrons. So what about the number of neutrons then? Well, we can find a number of neutrons if we know what the mass number is for that particular atom. So the mass number, which is abbreviated A, this is the sum of the number of protons and the number of neutrons. So if I do a little bit of math on this, right, I can now say that the number of neutrons is simply the mass number minus the number of protons. Okay, so this is critical in determining these numbers. So sometimes you might be given a couple of these or one of these. We can calculate the others. So the protons and the neutrons, okay, because they are found in the nucleus, sometimes these are collectively known as the nucleons. We don't see that as often, but you might see it here or there. So that's what it means. So when it comes to the nuclear or the atomic symbols now, let's take a look at what that actually means. So the nuclear symbol, we're going to have our elemental symbol written in normal cases here. So let's say X represents our elemental symbol. With this nuclear symbol notation, the atomic number is written typically on the lower side as a subscript that precedes the elemental symbol. So Z goes here, and then the mass number, the sum of the protons and neutrons, that goes on top. Okay, so for example, if we have an atom of, let's say, sodium. Okay, sodium has the symbol Na, and we have the elemental symbol as follows. So Na, and then sodium has 11 down here, and then 23 up on top. So what does that actually, what does that tell you? So before we get to what it tells you, one thing to note about the nuclear symbols that look like these, you're not going to see this. You will not see this notation on the periodic table, which you're going to get to a little bit later on. It's going to look slightly different, okay? But this is known, this particular arrangement here is known as the nuclear or the atomic symbol, and that looks slightly different than what you actually see in the entries on your periodic table. So for sodium, we can look at these, the A and the Z, and figure out some numbers. So Z here, okay, that's your atomic number, and that is the number of protons, which is 11. Okay, so there really is not a whole lot you need to think about that. It's given to you in green and white in this case. Now, because this is an atom, this means then that the number of protons that we have, which is 11, should also equal the number of electrons. Okay, so we have 11 protons, we have 11 electrons in this. The mass number here, 23. So 23 is the sum of the protons plus the neutrons. So then our number of neutrons would be 23 minus the number of protons. So 23 minus 11, that would give me 12 neutrons. Okay, so I can calculate each of the subatomic particles if I'm given the nuclear symbol, or if I'm given these numbers, okay, I can now put together my nuclear symbol. So going in the reverse direction if I wanted to. So I want to touch on one thing briefly before we take a look at isotopes. So in a typical periodic table that you might be provided with, such as this one shown here, if I look now in the periodic table entry for sodium, right, you'll notice that the numbers look a little different. So here, this is sodium highlighted in green. You'll see the 11 written on top, and that is the atomic number. Okay, so that's what I was saying before. The nuclear symbol notation looks a little different than the periodic table entries. Okay, so in the periodic table, and this particular one, that 11 up here, the whole number, that is your atomic number, which is a number of protons. You don't see the mass numbers on the periodic tables. These numbers underneath, typically decimals, those represent something different, which we'll get to a little bit later on. Okay, so on the periodic table, the atomic number is usually here. It's the whole number. So when it comes to identifying or calculating the number of subatomic particles, we can use the nuclear symbols to quickly figure that out. Or if we're given the nuclear symbols, we can work backwards and put together the nuclear or the atomic symbols. Now, there's a characteristic of the atoms that that is very, very important, and that's the fact that there's a possibility of the elements existing in in two or more what are known as isotopes. And what isotopes are different forms or atoms of the same element that have different mass numbers. Okay, so you can think of it, sort of as an analogy. If you think about a rice grain, right, you can have different types of rice grains, long grain, short grain, whatever. It's all rice, right? So it's the same thing, just have different types of it. So isotopes are kind of similar. You have the same type of atom, but they can be slightly different. And the way that they're different from each other is they have different mass numbers, which in essence means that they have different, oh, I'm sorry, they have the same number of protons, but different number of neutrons. Okay, so if we go back to our periodic table over here, okay, if I look at an atom and I tell you that the atomic number for this particular atom is 11, what that means is that atom is sodium. It's Na. It can't be anything else. Okay, and that's really, really important that you know this. The atomic number is the thing that defines an element. Okay, so the atomic number, which is the number of protons, it tells us right away the identity of that particular element. If an element has atomic number 3, well, that would be Li, which is lithium. If it has atomic number 30, that would be zinc, Zn. If it has atomic number 6, that would be carbon, C, and so on and so forth. You change the atomic number, if you have a different atomic number, that's a different element altogether. So keep that in mind. When we talk about isotopes, we're talking about atoms of the same element. So they have the same number of protons, but they have different numbers of neutrons. So for example, if I give you the following notations, if I have H, 3 and 1, I have H, 2 and 1, and I have H, 1 and 1. Okay, and if I then were to calculate the number of protons, neutrons, and electrons in these, all right, for my first one here, we'll do this one in yellow. Okay, the atomic number here is 1. So that means I have 1 proton. These are all atoms, by the way. So if I have 1 proton, I should also have 1 electron. The number of neutrons is simply the difference between the mass number and the atomic number. So 3 minus 1 gives 2 neutrons. If I look at my second element, this one, second atom, that one, my atomic number is still 1, right? And that makes sense because it's hydrogen. Hydrogen is atomic number 1. For atoms, number of protons equals number of electrons. My number of neutrons, then, the difference between 2 and 1 is 1. So I have 1 neutron in that atom. If I take a look at the last one, again, atomic number 1 means 1 proton. I have 1 electron. And now my number of neutrons is the difference between 1 and 1. So 1 minus 1 gives me 0. So these 3 atoms, these are isotopes. These are all isotopes of hydrogen. Okay, they have the same number of protons because they are hydrogen. They have 1 proton in every single example. Because they're atoms, they also have the same number of electrons. How they are different is in their number of neutrons. So this one here on the left has 2 neutrons. One in the middle has 1. The one on the right doesn't have any. Yeah, that's how we can identify isotopes of the same element. The way that we designate the differences between, or to designate the different types of isotopes, you can see them a couple different ways. So for example, if I have hydrogen like this can also be written as just H, and with the mass number 3, right, we can omit the 1 here because that's understood to be 1 since it is hydrogen, right? If you look up hydrogen on the table, atomic number is 1. We can also write the isotope as hydrogen dash 3, where we have the name and then the mass number, or just H dash 3, the symbol, chemical symbol, elemental symbol, and then the mass number that comes after it. So all of these notations, all of these ways are just different ways to represent the same isotope. So these are isotopic designations. And you'll see a combination of these all throughout your book and Alex online and elsewhere. Okay, so let's do the isotope that has a mass number of 2 just to compare it. So this would be H21, our normal nuclear or atomic symbol. It could also be H2 like that. It could also be hydrogen dash 2, or it could also be H dash 2. So the notation, interpreting what's given here is important, right? We can easily leave out the atomic number because we can look it up on the periodic table, right? So sometimes you don't see it in the designation.